I'm Matthew Sandoval, and this is my video for Lab 2. There are 5 parts to this lab: the introduction, the experiment, the code, the discussions, and the conclusion. The purpose of this lab is to determine, using the correct fundamental principles, the effects gravity and drag have on falling objects. The fundamental physical principles and models used in this lab are Newton's second law, weight force, and drag force. Newton's second law allows us to derive the position and velocity update formulas from the equation of net force, which is change in momentum over change in time. The average velocity, position update, velocity update, weight force, drag force, and net force equations are all vital in the computational portion of this lab. The system was a pair of Nike socks. Surroundings are my hand, gravity, drag, and the floor, and an important assumption that can be made is that the object did not travel in the X direction. For the procedures lab, I filmed myself dropping a pair of Nike socks falling from the height, which was about 70 inches. I then analyzed the video and tracker, and it allowed me to calculate values needed for the computational portion of the lab. After editing starter code and GlowScript, I was able to create 2 computational models. I then compared the data from tracker and both computational models in a Google Sheet that allowed me to plot the position versus time of all 3 of these cases. After inputting my film into tracker, I was able to come up with initial conditions that were needed in order to create the computational portion of the lab. These conditions were the observation start time, which was 0 seconds at frame 0, the sock's initial position, the sock's average velocity, the time of last observation, which was about 0.6 seconds at frame 30. The first computational model I created was the model that depicted the socks falling with no drag, aka just with the force of gravity. The mass of my socks was 14 grams, which translated to 0.014 kilograms. Both the initial position and velocity were found using tracker, and I inputted those accordingly into the code. Delta T was set to a time that matched the frame rate of my video, thus allowing the video and the code to be more accurate to each other. G is the gravity constant, aka 9.8 meters per second. Because this computational model only relies on gravity, I set the drag constant to 0. I set the while loop to end when the time is greater than the amount of time that the tracker video lasted. This again creates less discrepancies between the video and the code. I then created 3 variables: force of drag, weight, and net force. For the force of drag, I used the drag force equation. For the weight, I used the weight force equation, and the net force is just the sum of both of these forces. In each iteration of the code, the ball velocity and ball position will be updated using the position and velocity update formulas as per Newton's second law. This code also includes arrows that represent the vectors of the gravity and the drag force. In order to calculate the scale, I just used the distance fallen over the magnitude of the weight force. In the computational model with no drag, gravity is the only force acting upon the object. Because this force is constant, this also means the velocity will be constant, which is what is shown. The second computational model I created was a model with drag force and gravity. Only one change was needed between this computational model and the last one, which was changing the drag constant. The value of this drag constant would be found simply by testing values until I found one that would allow the final position of the system to end similarly to the final position on tracker. Since drag and gravity now act upon the object, velocity is no longer constant, as you can tell by the slope, which has a slight curve instead of just a straight line. The slope does flatten out over time, which relates to terminal velocity. The graph to the right depicts the distance fallen over time for each of the 3 models. Time passes, each one seems to differ slightly from the other. Computational models seem to have similar velocity for a larger portion of time during the fall, but the model with no drag falls further. This is due to obviously there being no drag, meaning there's no force to counteract gravity, thus allowing the object to move further in the same amount of time. The model with drag and the observed tracker position line up closer towards the end of the duration of the fall, because both illustrate terminal velocity and both end at the same position after they fell. Most of the discrepancies in the graphs can be contributed to errors made during the lab. Obviously, there are human errors, which could have occurred in coding, placing position points on trackers, rounding errors while calculating values, filming errors such as the angle of the camera and the frame rate of the video. Also, while it was assumed there was no motion in the X direction, this is obviously not how the observed motion would actually be. Because the computer models only track vertical motion, their positions and drag forces would differ slightly, causing some inaccuracies. The computer models don't take into effect object shape or what effect drag would have on that, or rotation of the object during the fall. The first question is, which model, if any, depicts terminal velocity? While the computational model with no drag does have a constant velocity, this model does not consider drag, therefore it cannot be said to illustrate terminal velocity. The computational model with drag, however, does illustrate terminal velocity as it depicts a velocity steadily approaching an asymptote around -5 meters per second squared. What would happen if the object were thrown down instead of just dropped? I simply increased the y component of the initial velocity in my computational model towards the negative direction. This increases the initial velocity of the object. So despite having a higher initial velocity, the model where the object was thrown instead of dropped still reaches a terminal velocity around -5 meters per second. It is important to note, however, that both models will eventually approach the same terminal velocity, but the model that was thrown will depict this velocity sooner.